Hello, everyone. So we will start with this section of CO2 conversion technologies, and I'm Alessio Foco from CNR, as I told 1 hour before. And the first presentation will be from Sahal Wakel. Salwa. Yes. Okay. From University of the Basque Country, and she will discuss about photocatalytic and surface consequences of the thermal treatment of nature on carbon nitrates for CO2 to CO conversion. So the floor is yours.
Thank you for the presentation. Good morning, everyone. So today I'm going to show my latest results on thesis for CO2 to CO. So just a super quick overview of the impacts of CO2 emission. As you know, the contribution to global warming, because we have a 50% more CO2 in the atmosphere than for the era pre-industrialization. We also have temperature rise projection. By the end of the century, we're planning to have 1.5 degrees Celsius, but we are almost going to have 3 more. Due to this, we are also going to have sea level rise. Greenland is losing tons of ice per year. Moreover, about the oceanification, we are losing a lot of biodiversity. And following up to this, we are also speeding up the extinctions of a lot of species that we know nowadays. So we need somehow to reduce all these emissions. So the most common ways to do this is the CO2 capture, making it to fuels or valuable chemicals. So for this, we use always catalysis. So in my research, we're going to highlight on catalysis. I will speak about photocatalysis. I don't know if you all know how photocatalytic reaction works, but catalytic reaction that uses external light as energy source. Photocatalytic reactions has 4 main steps. The first one is the light absorption of the material to generate electron hole pairs. The second step is to separate these side chairs in order to get them on the surface of our material. And the last one is using these charts for redox reactions. This will be how a perfect photocatalytic material will work, but we also have the problem of recombination of these electrons and holes. This recombination will lead to a deactivation on the efficiency of our reaction. So we will need to find some materials and somehow modify them in order to have less recombination of these electron and holes. So the materials that are used in photocatalytic reactions are mainly semiconductors. Between all the semiconductors, as the widely known titanium or zinc oxide, we decide to use graphitic carbonitride, not only because it's an eco-friendly material, also because it's able to absorb light. Moreover, it has a conduction band that is able to reduce CO2 into CO. Our problem is that the carbonitride by itself recombinates a lot of electrons and holes, so we are going to modify it somehow to have a better activity in our reaction. Our goal of this project, is thermal coupled photocatalysis, and we want to operate at low temperature. Also, we want to pave the way to start working with CO2 and water to get CO, but this is just the main first step. So we have our carbonitride synthesis, and we are going to dope it with different amounts of platinum between 0.2 and 2%. This platinum not only will act as an active site, it will also act as an electron sink. We will make a nitrogen pretreatment in order to remove possible impurities on the surface of our material. And as the case step, we will make a hydrogen pretreatment at 2 different temperatures and see how this is affecting to our catalyst and also how this affects to our plastic. And see how is this affecting to our CO productivity. So how are we synthesizing this carbonitride? We start from melamine and we make a polymerization under nitrogen atmosphere at 550 degrees. We wash it in order to remove melamine that has not been polymerized, And we have our carbon nitride. And for the metal impregnation, we are following the wet impregnation method using a platinum chloride precursor. We evaporate the solvent, let it dry, and did this nitrogen pretreatment to remove the chloride that could be present on the carbon nitride. And finally, these two different temperature hydrogen pretreatment. Later, we see our carbon nitride to be able to test this in our reactor. So, which is the design of our reactor? We have a feed with hydrogen and CO2 where it gets mixed and later it goes to our reactor. In this case, our reactor is able to hold temperature and pressure. And we also work with the xenon lamp that is simulating the solar spectrum. We work in a continuous way and we analyze everything with a microscope. So, how is the hydrogen pretreatment affecting our catalyst on CO productivity? First, we saw that when we were treating our material at 450 degrees in dark conditions, we saw the trend of our reaction was going down. But in the case of the 250, we saw less productivity and also a little increase. But by the moment we put light on each samples, we see a completely different trend. We also see a little jump in the 250, and the trend was still going up. But in the case of the material that was treated at higher temperature, we not only see this increase in production, we also saw a stabilization of the reactions. So we know that there is an effect on the catalyst, depending to which temperature we are using. So we decided that maybe the platinum was changing. We made an XRD of all these samples for the one that was treated at lower temperature, and we barely see platinum on it. But in the case of the other one, we started to see few peaks that corresponds to platinum nanoparticles. So okay, we know that the platinum structure is changing somehow. So we decided also to make an XPS analysis of this metal, and we saw that treating in at 250, we were getting platinum +2, and also within EDX, we saw that we were generating a platinum +2 monolayer on our catalyst. Nevertheless, in the hydrogen pretreatment, this was not the case. In this case, we were working with metallic platinum, and also we were generating nanoparticles on the catalyst. So now we know that we have platinum +2 and also platinum nanoparticles, but we were also wondering if the carbon nitride gets affected somehow. So we decided also to make an XPS analysis of the carbon and nitrogen spectra. And we saw that when we were treating at higher temperature, the carbon and nitrogen binding energy was shifting to a higher binding energies. This means that there is a modification on the structure of the carbon nitride. So we check the carbon nitrogen ratios that we are having in each of the catalysts. And we saw that when we were treating at higher temperature, this carbon and nitrogen ratio was getting low. So we checked with TGAMS what was going on during its hydrogen pretreatment. And we saw that there was a carbon or nitrogen loss in it. So because we saw that we were producing methane and also ammonia. This means that when we were treating at 250 degrees, according to literature, we are generating this type of vacancies on the material. And the 451, we were not only generating this type, we were also generating this. So, okay, now that we know which type of vacancies we have, which type of metal we have in the material, want to know how is this affecting the charge recombination of our catalyst. So for that, we will measure the photoelectrochemical characterization. So in this case, we start with the photoelectrochemical impedance spectroscopy in order to know the electron flow resistance. In this kind of technique, what we know is that when the arc of the radius is smaller, the electron flow is best. So in this case, the samples that are at the bottom that were the ones that were treated at higher temperature saw best electron flow because there was a lower resistance. Following up with this trend, for the transit photocarbon response, we were measuring the charge utilization of our catalyst, and in this case, a higher intensity will mean a best charge utilization. So in this case, also the material that was treated at higher temperature had a better response to the characterization technique. Finally, to measure the charge recombination intensity, we know that in this case, with the photoluminescence technique, a higher intensity will mean a higher charge recombination, and in this case, our material that also was treated at 450 was behaving best. So once we have all this electrochemical characterization, we need to know if this is also matching with our catalytic results. If we start with the catalysts that were treated at lower temperature, we barely see any difference between adding 0.2 or 0.5 platinum on the catalyst. We only see a bit of upward trend when we sign on light. But if we start at 225, we can see that the material with 2% of platinum is behaving quite best than the other ones, and also there is a really significant jump. We also know, at the end, we realize that this could be because during the reaction, our platinum plus 2 is converting to metallic platinum, and this will enhance the reaction. But if we compare with the other material, we see that in dark, this is deactivated. But when we sign on the light, this starts to jump a bit and also to stabilize the reaction. And by the moment we increase the temperature, we are also able to see this trend for the 0.5% with platinum in our catalyst, but the one that behaves best is the 2% of platinum treated at 450 degrees. So the conclusion that we got from these catalytic results is that the light boosts and stabilizes CO productivity. Moreover, higher temperatures improve separation and reaction kinetics. This means that some recombination is not always best when we increase the temperature. Maybe we will reach a point where an increase in this temperature will become a higher ratio in recombination. Also, that the catalytic activity depends strongly on the platinum oxidation state, and optimizing this catalytic reaction temperature scale to have a best photocatalytic reaction. So the conclusion that we can get from this research, we also have this article if you want to take, we got that we start with this material with some platinum chloride on it, we treat at this temperature with hydrogen, we are able to remove all these chlorides that were present on the metal precursor, and that we were producing methane and ammonia, and that we finally end with a material that had this type of vacancies, and also we were generating platinum plus 2 and a platinum plus 2 monolayer. And in the other way, we were getting this type of material generating these two type of vacancies, metallic platinum and also metallic platinum nanoparticle formation. So the conclusion that we can get is that with this type of material, we are having higher CO productivity. We decrease the electron hole recombination, we improve charge utilization, and we have an overall enhanced photocatalytic activity. So I would like to thank the Qatar project for letting me be part of this, and also the Supreme Group from the University of Basque Country, because without them, anything of this would have been possible. So this is my contact in case you have any doubts or whatever. So thank you very much for your attention.
Thank you a lot for being in time, exactly in time. So any questions? Yes, I see from this.
C3N4 is a very interesting catalyst. Have you checked your C3N4 in terms of its carbon to nitrogen to hydrogen ratio?
The C3 and 4, sorry, I'm not.
Have you analyzed the C3N4 data?
Yeah.
In terms of its carbon to nitrogen to hydrogen ratio.
Hydrogen, no, we don't analyze hydrogen ratio.
What is C3N4?
What?
It's not C3N4.
No, it is.
No, it isn't.
Ah, why?
Because the composition varies.
Okay.
And we've made some really nice C3N4 with ideal ratios, and it's not as good as
Yeah.
something that's not a stoichiometric.
Okay.
So it's worth just doing the CH analysis.
Okay.
And if it's not quite C3N4, it often works much better.
Okay.
So we spent a lot of time making it really nice, and it wasn't as good a photocatalyst.
Okay.
So it's it's amorphous. It's not perfectly C3N4, and everybody assumes it is, but it's not quite.
That happens in many systems. One thing is what you see in the slide, one thing is reality.
Yeah, and people get better results than us, and they wonder why.
Yeah.
That's because they didn't make it themselves.
Okay.
So,
Okay, thank you.
but certainly, and it's quite easy to do, just straightforward analysis. Not-
Okay, we see it then.
See, it's-
Yeah, okay, good.
The data shown on the carbon nitride ratio, how it's changing with reaction, were taken from this elemental analysis.
Yeah.
So you showed some data on the carbon nitride ratio
Yeah.
made through this CHN analysis. And it is true that it's changing even through reaction,
Yeah.
and that we don't start from a perfect ratio.
Yeah.
Yeah, you get a better bandwidth. It's not
Yeah.
quite.
Yeah.
Yes, yes.
Yeah.
So this is very common.
There's another one from Permeder.
Nice presentation, Salva. So I was wondering what is happening with the XPS.
Oh.
So you see that it's moving, it's shifting to higher energy values
Yeah.
because maybe it's also changing the
This.
electron density of the carbon nitride, or
Yeah, it's also changing. I know I don't remember how exactly it was. It's in the article, but yes, we realized that the electronic configuration was changing. We also have another characterization technique that support the theory. So yes, we know that something was going on with that. Yeah.
and the last question. When you did the catalysis,
Mhm.
you did also the catalysis with carbon dioxide labeled isotopic.
No, we only mean with carbon monoxide. Yeah.
Thank you.
Thank you very much for your nice presentation. I would like to ask you about the final carbon dioxide conversion and the yield. Carbon monoxide. What is the yield of carbon monoxide? Because we use very expensive materials, platinum.
Yeah, no, I know the conversion on the yield is not really high, so that's why we don't show in the presentation. Yeah.
Because the production rate of CO is very, very low.
No, we know. This was a bit, we started with this because we wanted to extrapolate all these results for CO2 conversion with water. So it was like at the beginning of the research. Yeah.
And also, I would like to ask you about the stability of carbon nitride in the presence of produced water. How the water affects the stability of carbon nitride at high temperature.
Actually, it was quite stable. I don't have here, but it lasts for a long time, the reaction. I don't remember how many hours exactly with this, but I don't know, maybe for 3 days for sure that this was stable. Yeah.
Okay.
Yeah.
And also maybe it is a good point to examine the effect of pretreatment conditions, examining the reaction measure. To treat the catalyst under the reaction measure, because you have a reductive environment that is independent of starting from calcine or using conditions. At the end of the reaction, the catalyst will be reduced.
Yeah, no, actually, we also tried that, but we let this run for a long time at the reaction condition, and we know that not all the platinum was able to get reduced. We ended with a mixture between platinum 3 or platinum plus 2. Yeah.
Thank you very much.
Thanks a lot. Thanks for the presentation, the discussion. We'll move to the other part. Maybe for a couple of presentations. So now it's the time of Andrea Moranti from Politecnico di Torino. He will discuss about multiphysics modeling of OIM ceramic reactor for CO2 water electroconversion to light olefins.
Okay.
So hello to everyone. So my name is Andrea Moranti. I'm a PhD student in Frederick in Torino. And today I will try to describe our multiphysics modeling approach for coionic conductors, for ceramic coionic conductor, for natural fluid production from CO2 and water. In particular, these results are proposed through the Eco-Olefins project, which is a Pathfinder project, which is now in its third year, which tries again to say considers all of the process and tries with a coionic conductor which conducts both hydrogen ions and oxygen ions to produce olefins at the fuel electrode. So the central part is that we talk about today. In particular, we try to focus mostly on the modeling approach, but since we are at the third year, we're still missing some fitting data, basically, which considers all of the results from the other partners. And so most of the fitting we did was just from literature, which is not obviously optimized for the final goal of our project, but it will provide an idea of what we're working on. So basically the idea of the project, of the model, is from a fluidic, thermal, and in general, electric model is very state of the art. So it's typical of a solid oxide cell or a PEM. What changes mostly is the electrolyte model, which is different from the state of the art, which usually just consider the specific resistance. And also the reactions model, because at the electrode we will consider all of the electrochemical and chemical production on the different byproducts. So in particular, we propose two geometries in the framework of the project: a planar geometry of 5x5 and a tubular geometry, which is 20 centimeters long. With the most, let's say, innovative part associated with how coionic behavior is conducted. Actually, we don't really have just two ions in this kind of material, which is usually barium doped, zirconate and cerate. We actually have three different ions. So the hydrogen ions goes from the positrons to the negatrons, and that's what we produce the hydrogen and the olefins. The oxygen ions goes from the positron to the negatron, and so we're trying to remove them in order to basically improve the olefins production by removal of water during production. And then we have the electron holes, which are just actually allocation. So we would like to reduce them as much as possible, but especially the barium yttrium, which we are considering for this model, the electron leakage is actually pretty high. So the governing equations are the Nernst-Planck-Poisson equation, which allow to assess the single flux for each single ion, as well as assessing the conductivity through Nernst-Einstein equation. The boundary conditions consist just in the voltage assessment, in the voltage definition, and on the concentration of the ions of the boundaries through the gas and perovskite equilibrium. We can also consider just a transient behavior, but for now we just consider equilibrium for simplicity. And then let's say we can therefore assess how much of each single ion is flowing through the electrolyte and assess the coionic behavior. In terms of the rest of the model, actually the final goal of the project would be to, let's say, kind of describe through electrochemical Button-Warmer definition how the electrochemical we could produce olefins. At the moment, we are still missing this fitting because we don't have the electrochemical performance still. So for now, for this model, I will especially just focus on the hydrogen and the oxygen removal. And then at the electrode, we also perform Fischer Tropsch method of olefins, basically through that from literature, usually using cobalt or iron, and assuming that the reaction occurs in the porosity of the electrodes. Again, for the fluidic electro and thermal model, it's more state of the art. So it's the typical governing equations. I will start by focusing on the planar cell. So it's a 3D cell, which is like 5. And in particular here, I'm just focusing on the let's say the first part, which is the hydrogen production, basically. So here I'm not, for now, we're not producing olefins. And the idea was to try and assess here, make some sensitivity on how just the electrochemical processing is optimized. So we can perform sensitivity analysis in terms of temperature. So higher temperature obviously will improve the electrochemical performance and hydrogen production, which can be the counter, let's say, opposite to the Fischer troph. So we will have to find obviously a trade-off. The goal of the project is to reach good performances around 400 degrees heat. For now, we usually work at 500 to 600 in the typical problem reactor. So there is let's say a big gap from the project. As you can see, in fact, from up here, let's say the performance really decreases a lot below 500 degrees Celsius, which is also important for the results that we show later. The electron leakage as well, though, is worsened when higher temperature is reached. So it's another aspect to take into account. Regarding water contents on the, let's say, the positive side, so the anode side, higher water content will improve the performance, but while the effect on the cathode side is not that high, which obviously will differ when Fischer trophs and olefins production are introduced. In addition to the sensitivity and the performance according to different operating conditions, also the geometry can be very important, especially again when reactions are performed because of the high exothermicity and endothermicity, so in general the thermal management inside of a cell. So we can perform different let's say different configurations in counter and closed flow to see and let's say minimize the temperature gradient, which could also break the cells, which are not that resistant, obviously, in terms of 1 megapascal, which we can survive. And they're usually characterized by like fraction toughness of 0.4 megapascal per square meter. And so for an electrolysis, we just found that cross flow was actually the best in terms of gradient variation. But now we want to focus more also on the olefins production, and especially on the new geometry, which is the tubular. So at least I can introduce both of them. And the tubular is considered as a tubing shell configuration. So we have one tube inside our shell. In the inner tube, we are producing olefins, which we can extract and eventually recirculate if we want to have multiple passage in the reactor. And the outer flow inside is just water and oxygen. So with the ideally also since we are also basically separating oxygen, the also idea of let's say economically valorized this byproduct. In the outer shell, we also have a metallic porous material to try and again improve the thermal management to changing the outer flow ratio. And the idea also is for eventually scaling up the technology, which would be more risky made thanks to the modular behavior of this cell. But again, so now we want to focus actually on the olefins production, in particular, so in everything that's happening. So again, we are working on the, just went out, that as I was saying before, at 400, 450 Celsius, the hydrogen unfortunately is not highly produced. So again, this will have an impact because it will decrease basically the hydrogen which will react for the olefins production. As you can see here, in fact, the hydrogen is basically with this current say ratio is basically always and consumed as soon as it is produced. And in particular, this operating condition, the reverse vertical shift, so the CO is what is improving the most. When higher temperature are used, though, we can see that some of the performance used are let's say increased. I mean, all of the reactions are increased, so the idea should be or just thermodynamics or just to again increase the hydrogen production. So basically, just more reactants. Just to try and understand what's the actual reason, we basically, let's say, fictitiously improved the performance. So we have kept the same. We have basically kept the same temperature, but we have tried to increase the hydrogen production in the electrode side. By doing so, we can see that actually the performance again are improved again, which means that basically what was most important was that the simply increased hydrogen production was increased in the olefins synthesis, which means that depending also on the sensitivity of the materials, having higher temperature, it increases a lot the hydrogen production can be beneficial, even though the thermodynamics and the kinetics could change even negatively. after this aspect, we then introduce the actual, let's say, goal of the product, which is the co-ionic. So we are trying to see what happens when we are also able to basically extract the oxygen while it's produced to reduce basically also the water consumption. And you can see how, in fact, the water consumption is decreased with all of the performance which are increased except for water consumption, which, let's say, justifies the goal of the product of having a co-ionic conductor. Therefore, so what can we conclude from all of this data? So we can perform multi-physics modeling, which allows to consider all of the aspects, both thermal, fluidic, chemical, and electrochemical, and which allows us to extract different, basically different KPIs in terms of performances, just on hydrogen production or just on olefins production and so on. What's important to do is, again, fit with the project results. So like the catalysts that have been developed in the project have a lot higher conversion, faster kinetics, and higher yield than the ones we're using in this model. And also let's see, it's important to optimize the structure, again, in terms of temperature distribution. The temperature reached in our model up to a 300 degrees Celsius difference between the inlet and the outlet, which is a lot for a cell. And also the operating conditions are important in terms of temperature, but also what we found was the importance of basically the flow rate. So like basically just decreasing the flow rate obviously will increase the residual time in inside of the reactor, but very low flow just increase a lot the temperature because we couldn't remove the produced temperature. So even just recirculation can be very helpful. So yeah, we are the team that worked on this product from the Polito, but the team itself also works on a lot of different topics that you can see here in terms of electrochemical, thermochemical, CO2 capture, and so on. And I would like to thank you all for your attention.
Thanks, Andrea, for the presentation. So we have room for questions. Go for it.
Thank you very much for the presentation. I have a question related to your future work, because you brought fitting the results. Why you need to fit the results?
So because basically, I mean, this model is let's say is not available, say, everywhere in literature. What we do is basically we do a combination of different models altogether, and each performance is validated and calibrated with specific materials. So for example, the electrochemical performance uses a proton conductor ceramic properties, which are intrinsically characterized, especially at low temperature, by a not very high oxygen ionic conductor. So like to reach, let's say, oxygen conductor, we have to reach at least 600 Celsius, which are very high for olefins production. So obviously, when we will have, let's say, a co-ionic membrane, let's say the ratio between hydrogen ions and oxygen ions will be a lot higher, ideally 1:1, which would improve the co-ionic behavior. And also efficient troughs, basically, we have the data we are using now is for high pressure, for different, the idea of the project is high pressure. So in general, like, obviously, a model, we can put everything inside. So a goal of a model is just to provide mostly feedback for the other partners. But if you want to get more realistic results, we have to fit the different, we have to calibrate the different performance.
Okay, so you to put for example, right kinetics and
Yeah.
Okay, I understand, because the kinetics of Fischer-Tropsch are not very easy, are always lumped, right? So perhaps you can use the model also to understand.
I mean, actually, we have two models. One is just so the one I'm using now is just lumped steps. Okay? We also have microkinetics, because the idea could also be that basically they absorb the ion, which then can be used in the Fischer-Tropsch. And the microkinetics could also just be used in the electrochemical, because the determining step and so on, we expect hydrogen to be a lot quicker to actually produce. So it could also be that just hydrogen is so quick that just we produce and then become just chemical, not even electrochemical necessarily. But yeah, that would be.
Okay, thanks.
Okay, thanks a lot. And question, curiosity from the audience?
Okay, thank you for the presentation. So So I was curious what you say at the end, that you have also modeled use of the flow,
Yeah.
the flow rate. But what happens when you reduce the flow rate? We increase the temperature, but also increase the production of olefins.
Yeah, because the kinetics, I mean, we just allow all of the kinetics to basically.
Higher temperature.
Yeah.
And also in your model, you say that you were the reaction that you were considering. You were also considering as olefin source the composition of the alcohols. No?
And
But you didn't consider the reactions to form the alcohols.
no, actually, I won't. Those I'm just oppressed in the document. Otherwise, it's gonna be too. Because it's gonna be all of theory. So that is to get some results. Yeah.
Okay, and the last one. In your models, you were checking you say that as much as increase the hydrogen, it will increase also the production of olefins.
Yeah.
But in your model, the concentration of hydrogen is always low. How do you know that it has increased with the temperature has increased the amount of hydrogen because it's always on zero?
That actually also depends a lot on how we're evaluating the results. In terms of, so since it's a 3D model, obviously it changes also a lot the distribution, all of the axes and all of the radius. So for example, here I put the cut line for the assessment of the results very in a position which again provides very, again, most of the olefins production, but it changes a lot on the radial. So even though it's not shown here, I did cut line of the different let's say, values, and I saw the distribution, and you can see basically this, what I said, you can see that. I just want to show it. But.
Thanks. Any other question? There's still a couple of minutes. If you're just a question, you said it about the hydrogen. So increasing the hydrogen, you will increase the production. But are you also increasing the hydrogen loss at the end of your process? Or you're recirculating the hydrogen? Or what happened?
Yeah, at the moment, yeah, we're not. I mean, the model this is not recirculating. So with a recirculation, would be extremely good. So like now it's just a single pass. So single pass, and then we.
And in the project, you're thinking about the recirculation, or it's just like it's a concept trying to see what works?
I mean, for sure it's a proof of concept, but ideally, if we could recirculate, ideally after, it also depends on the final step of the olefins purification. So if after the purification, basically we have flow condition, technical condition, like if we're not doing, cryogenic, the flow is at 20 Celsius and so on, we have to heat it up again after 100. Technically, we have to see if it convenes or not. So that's okay.
Okay, better. Okay. Yeah. If there are other use this, we can go forward. Nice time for Werner. And thanks for it. Thanks for this. Now it's time for Erwin Seppeldovi. We will discuss about recycling CO2 from gas through catalysts using affordable materials. So actually today was speaking about you will not use ruthenium, right?
No.
You're not going to discuss about ruthenium, but other two affordable materials.
Actually, I'm talking something about ruthenium, but
Yeah. Not too
I
much.
was not aware of this. But no problem. Really short.
Yeah.
So thank you for the organizing committee for inviting me and for giving this talk and talk about my life a little bit. So initially, first of all, just introduce our group that is called HG Energy. We are based in Valencia, and especially we are located in the chemistry department of the UPB, but also in the ITQ. Okay, many of you maybe they have collaborated already with ITQ because it works a lot in catalysis. But especially what does our group do? What we do is we prepare materials for many applications, but we are specialized in the synthesis of photoactive materials. We apply this material basically in different applications as Salva was showing, photocatalysis for water splitting, mainly also for waste valorization, but also in the field of photothermal catalysis, we are quite active in the conversion of CO2 to fuels. And also we are trying to do something with the nitrogen fixation, but the success is a bit limited on this field. So what is our aim, our goal, our target of our group is to use the sunlight and heat energy to push reactions. Okay, and yeah, this is what we do. So we try to use this to valorize CO2. This is just an example of the carbon budget of the Australian government. This is what they consider that they are going to the emissions that they consider they will have along the year. So if you are able to sum up all the tons, this is million tons of CO2 that they are wasting. The red ones are the anthropogenic. The blue ones are the natural emissions. And as you can see, if you are able to sum all the contributions and also all the natural processes that remove CO2 from the atmosphere, you will arrive to only in Australia to 1,000 million tons. If I was able to use only 1% of this amount of CO2 in Australia, I was doing numbers yesterday, and I can be able to do 3 million tons of octane, okay, of gasoline. So we are all behind valorizing CO2 because of this, because we can just using a bit amount of this CO2, we can generate a lot of economical beneficial and social beneficial, and also most important, the environmental. So this is more or less our idea. Our idea is to trap the CO2. Okay, that's generated in the industry and in the city, in the human activity. And then by, in this case, by solar energy, but also using other renewable sources, try to convert the CO2 into fuels again. Okay, so it's important because you will know this is a way to achieve the carbon neutrality. Also, it's very important because this is the ultimate of circular economy, because converting CO2 again to fuel that can be reused has a big potential, energetic, but also economically. And also, in the case of the European Union, this will be made possible to achieve independency of fossil fuels from countries from outside of Europe. So, the IWSCT, we are participating in the Dam for CO2 project. Okay, and the main goal of the CO2 project is to purify CO2 from flue gas and to convert this CO2 to C4 products. Okay, it's very challenging because the conditions that we have to do the catalysis are not the best to achieve this target. So what we have to do is to do a very good catalyst that could be able to do these reactions. So the philosophy of Dam for CO2 is first use a membrane to separate the CO2 from the flue gas, and then use a second membrane that we call the catalytic membrane, able to convert the CO2 to alkanes. Okay, so to be able to produce alkanes, you need to perform two reactions in a consecutive way. The first one is the reverse water gas shift, and the second one is the fission process. Okay, so we have a lot of elements in the periodic table that we can use for this catalysis, but the European Union, to make this more interesting, funded almost all. So this is good for us because limiting us the amount of elements that we can use, it can give us a possibility. Okay, so for using this kind of catalysis, we need the active size, of course, the active size for the reverse water gas shift, that we can use metallic nanoparticles as allow I did with the platinum, but it's not allowed, so we can use only silver and copper. We can use oxides, metal oxides, as iron and chromium, that in specific ratios of hydrogen and CO2, they work very well in the reverse water gas shift reaction. But also you need the active size for the fission drops. The best one is cobalt, but again, it's banned, so we cannot use cobalt. So we need to dive into iron and nickel. These two catalysts, they perform very good the CO2 hydrogenation, but they are performing so good this reaction that they stop in methane normally. So to improve or to push the reaction to longer alkanes, you need to choose other metals, other, let's say, elements that push the reaction to this way. So one of these are the enhancers. We call enhancers that, as example, that we are using the manganese and the zinc. Because these enhancers, what they do is they are assessing the oxidation conversion, the redox conversion of the different active sites. And also then you have the alkaline ankyloterries that what they are promoting is the absorption of the CO2 on the metal and on the catalytic particle. Okay. So what we are doing in this project and normally in our group for converting CO2 is we are playing with the photothermocatalysis. Okay. Photothermocatalysis, what they use is the photocatalysis linked with the classical thermal catalysis. Okay. So basically what we do is we place together a light and heat for doing this reaction. And with this, what we are achieving is improvement of the reaction. Sometimes sometimes we can achieve like 3 or 4 times more efficiency. You will see that. So just briefly, the photothermal catalysis, you can have 3 possibilities, but you will never have one of these, something in between of them. So the first one is that you are using light just for heating the catalyst, okay, to achieve higher temperatures. The next one is that you are doing photocatalysis. Is as Saloa said, when you are using photocatalysis, you are promoting the charge separation, and this using these electrons and holes to promote oxidation and reduction reactions. So when you are doing photothermal catalysis, what can happen is that the temperature is just improving this movement of charges through the material, making it more effective. And then you can have a mix of both. That you have the formation of electrons and holes for the photo because the photo, but the thermal energy is driving also the reaction. So what we have been done for CO2 is we have been making reactions in continuous flow using a mixture of carbon dioxide and hydrogen. And we have been working around 250 degrees and 350 degrees because we are limited by our project conditions. And also the light intensity, we have played around with these light intensities. So this is just an example of a metal oxide that we have synthesized for the project. And this is a high entropy metal oxide where we have iron, copper, and zinc, and some traces of potassium. And what you can see here in the squares of red squares and blue squares, this is just the metal oxides, the pure metal oxides. Let's say copper and iron, or copper and iron, or zinc and iron. So then you can see in between the samples that are made of the 3 metals. So in the case of the difference spectra that you can see is the production of different products that you can find during the reaction. So here the first one is the carbon monoxide. So you can see here the gray line is in dark and the blue line is during light. So you can see that the introduction of the zinc or making the three metallic oxide will have an improvement of the CO2 of the carbon monoxide production, not really high compared to the initial material. But when we go to the Fischer-Tropsch products that are these ones, the methane, ethane, ethylene, propane, and butene, you can see that the introduction of the mixing of these 3 metals has a synergistic effect. And just to point it out, when you have a synergistic effect, you may have like an increase of, I don't know, multiply of the production per 5 or per 6. So you can see here that the most effective one is, in our case, is that when we have 5 times of zinc per 1 of copper. And what you can see here is that not only the productions of the Fischer-Tropsch products increases when we have the three metal composite, but also the response to light. Response to light has increased with the addition of zinc to the material, and is quite impressive because compared to dark and light, we have like 3 or 4 times the catalytic production, the initial catalytic production. So we can also make an idea of which is the mechanisms that are following the different reactions. The reverse water gas shift is following a photothermocatalysis. I mean, that is just following the light is only hitting the material, basically, because the increase is, there is quite a good increase, maybe of 60% or something like that, but it's not very impressive. But whereas the Fischer-Tropsch is following a real photothermal mechanism, in which light is exchanging the selectivity and making the reaction more efficiency. And also that the zinc, what is making the difference in our materials is that it's pushing the production towards the alkane products. Okay. So this is just what I was trying to tell you before in the formation of different catalysts. And just for ending, we are also very active working with MOFs. In this case, MOFs at the moment, or in the reaction conditions that we are working that are around 200 degrees, they are not acting as a real catalyst. They are more acting as a semiconductor. So what we are making is we are creating systems similar to this one, in which the MOF is the photoactive semiconductor that is using the light for creating charges. And then we are depositing metal nanoparticles acting as a co-catalyst. In this case, it's the ruthenium, sorry. Okay. So we have just presented you briefly 2 of the works that we have published recently. In these 2 works, we are using the MOF UEO66. And what we are doing in these 2 works is we are in one moment, we are changing the metal complex for other complex or mixing different metals. And also we are changing the ligand, and we are replacing this ligand for a nitro ligand, amino ligand, okay, amino tephthalic, something like that. And what we are making with the changes that we are inducing to the MOF is that while we are keeping the crystal structure, we are playing with the bandgap of the MOF, but also of the valence bands and covalent band position. Okay, so playing with this covalent band and bandgap, a covalent valence band position and the bandgap, we are able to increase the productivity of the composite. Just ending the last example. In this case, we are using the MIL 101 chromium. Okay, and in this case, we did the same. What we did is replace the chromium by iron, and we tried different amounts of ruthenium nanoparticles. The loading, we changed the loading, and we saw again this effect that the bandgap, but also the valence band, the covalent position bands, where they are located is very important for the overall photocatalytic result. And that's it. Just would like to acknowledge the guys that they are working very hard in the lab right now, I hope. And just also the funding for the different organizations, especially to the Ramon y Cajal. And thank you for your attention. Do you have any questions?
Thank you. Questions? Here we are.
Thank you for this great work. If I understood correctly, you are working without the membrane configuration, right? For this data? Or...
I only showed you the data of the catalyst, but we have also data with the membrane.
My question is mostly related to the time stream data, how stable the catalyst is, and especially to know how water affects. Because if I understand correctly, the conversions at which you are working are not let's say, generating a lot of water in catalysis. So I'm not sure if you have an idea of how water affects, especially Fischer-Tropsch steps, which are often inhibited by water.
So we have been, actually, we have done a lot of experiments on this regard. The good thing of doing the reaction in continuous flow is that you are removing the water while it's forming. So this problem is not less intensive as you have when you are working in batch. So in this case, we don't have the problem. This problem. These catalysts, the metal oxides, are quite stable on time, so they are very robust. The MOFs are less robust, and we have tried to do some experiments flowing the CO2, passing the CO2 through water, have some humidity, and we have seen that the Fischer-Tropsch part of the reaction gets improved. I don't know which is the reason. We are not sure. We believe that it's because you have some active sites that get oxidated. These active sites are the ones that are more active in this reaction. But we are not really sure. And the last issue is that when you are doing this kind of catalysis, if you stop the reaction suddenly without flowing argon, the CO2 that you are producing starts poisoning the active sites. So this is the main issue, or the reusability.
Any other question? Well, it would be strange to make question to you. We discuss. Thank you, almost all. Then, so thanks again, Herbert, for your presentation. And now the next speaker is Ruth Kortlener from Delft University of Technology and the Connect project, another project of the portfolio. He will discuss about operational efforts on CO2 and nitrate correlation for urea electrosynthesis. So please.
Right. Good morning from my side to you. I'm actually replacing one of my group members, Dr. Phil, who's the postdoc who actually did all the work. So all the credits of the work that I'm showing today will go to him. I'm not sure if there's a picture anywhere. Yes, awesome. Sorry. Thank you. All right, so we are working in the project on urea electrosynthesis, and specifically what I will talk to you about today is CO2 plus nitrate co-electroreduction to urea. So yeah, a bit about the background. So this could be an alternative process to make urea as a fertilizer, basically using waste input, so waste CO2, nitrate from waste sources, and using renewable electricity to power the electrochemical conversion. So basically what that means is you would be able to move away from fossil-based, highly centralized processes that exist currently, so the Haber-Bosch process that produces ammonia, and then the Bosch-Meissner process that uses that ammonia plus CO2 to produce urea. Okay, so clear that these are the advantages. You use waste CO2, you use waste nitrate, you use renewable electricity, produce in a decentralized way a fertilizer. However, there are still some key challenges out there in the literature. So there's a lot of varying Faraday efficiency, where I mean the selectivities towards urea that we reach in this reaction. And we also see large variations in the literature on the actual rates, the yield rates, so the product yields of urea that you make in the electrolyte. Okay, so if you look at the literature, there's been a lot of work on advanced catalysts, so complicated catalyst systems that produce urea. Mostly are copper-based, but sometimes alloys could be quite complex. And then at the same time, you also see that there's a lot of debate about the actual reproducibility of this reaction. So can we actually make urea? Can we reproducibly check whether we make urea? Aren't we having false positives in there in the quantification? So what we wanted to do is basically use a benchmark system to actually show or to see whether we could actually make urea, how much urea we make, and how do operating procedures basically affect urea production. Because if you look at we look at the overview of data, right? Here you see on the left hand, you see the Faraday efficiency, so the selectivities, and on the right hand, you see the urea yields for different reported systems. You can see they go all over the place, right? And then dependent on age cells, flow cells, they go all over the place. And of course, every study is using their own special catalyst. They use their own electrolyzer setup with their own reactor geometries, right? Can we do some work with a commercial catalyst systems, easily reproducible with a standardized kind of electrolyzer set? So in the work that we use a flow cell. So this is a commercial flow cell that we modified tiny bits. So we use a liquid electrolyte. So we have a liquid electrolyte on this side, so a liquid catalyte, and we have zero gap configuration on the anode side. So here is your cathode. This is a gas diffusion porous electrode. So your CO2 comes from the back. Your nitrate is in the liquid, right? Reaction takes place on this interface. Here we have a membrane. On the other side, we do oxygen evolution in a zero gap fashion. We use commercial copper, so commercial copper catalyst. And we specifically have a look at the effect of all the parameters in these electrolyzers, how they affect urea production. So here again, this is again an overview of the electrolyzer. Here you see the electrodes, the cathode, the anode, this gap. So this is a thin electrolyte gap, so 3 millimeters thick gap. This side is zero gap. And here are the reactions that are actually taking place in our system. So the preferred reaction that we would like to have, of course, is having this reaction of CO2 plus nitrate to go to urea. But simultaneously, of course, we also have CO2 reduction. So CO2 reduction, for instance, to carbon monoxide, but on top we can make a variety of different products. And of course, we can also have nitrate reduction itself. It's producing ammonia, but also producing nitrite. And this is the entire system. So basically, we measure the gas products in line. So all of the gas products that come out of the electrolyzer in line. And then afterwards, we take liquid samples of the catalyte to detect the amount of urea and other liquid products. So there's been a lot of debate on actual quantification, and in the afternoon there will be another presentation from this project on how can you accurately detect urea. Here I just want to highlight the method that we have been using. So we use urease method, where you have this enzyme urease that decomposes urea into CO2 and ammonia, and then we use ion chromatography to measure the ammonium in the electrolyte. You can see our method works quite properly, so we get quite stable calibration lines, so quite straight calibration lines, both in just pure water and in our actual electrolyte. So we're quite confident that we can nicely measure the amount of urea that we produce. Okay, so now let's have a look at all of the parameters in the electrolyzer and how they affect. So first, let's have a look at the membrane, right? So you can use different types of membranes in this system. Of course, we cannot use an anion exchange membrane because that would mean that all of our nitrate is crossing the membrane. But we can choose a cation exchange or a bipolar membrane. So if you use a look at the cation exchange and the bipolar membranes, these are the currents. So you can see with the not film, which is the cation exchange membrane, the currents are not very stable. But with the bipolar membrane, we are able to get stable currents. And if you look at the Faraday efficiencies, well, you see that the Faraday efficiencies do not differ too much. You see all of the major products that we would expect. Tiny bits of urea on the top, right? For both systems, you can actually see that the bipolar membrane performs a bit better than the cation exchange membrane for urea production. We see ammonia from nitrate production. We see nitrate from nitrate, nitrite from nitrate production. And we see some CO2 reduction products, so formate, CO, we see from hydrogen evolution. And here you can also clearly see why the bipolar membrane is more stable than the cation exchange membrane, because you can see that the pH and the conductivity in the case of the cation exchange membrane is not stable, while in the case of the bipolar membrane, it is stable. And that is basically due to potassium crossover from our electrolyte with cation exchange membrane. And of course, this bipolar membrane blocks potassium crossover, so we are able to keep a stable pH and stable conductivity, and also stable, as an effect, a stable current over our measurement. In the additional measurements, we all use bipolar membranes, and we had a look at the other kind of parameters. So here's the effect of copper loading, and you can see that the copper loading basically does not have that much of an effect on the urea Faraday efficiencies. But if you look at the yield rates, right, there's a tremendous effect, and that's of course because you normalize versus the amount of catalyst that you use. So if you look into literature, right, a lot of different loadings that have been used, but actually if you want to get a very high urea yield or a yield rate, you can do this mathematic trick that you have a very low catalyst loading, and then all of a sudden your yield rate looks really high, right? But like as you see, it does not matter that much what kind of catalyst loading you do. So you use for the actual performance of the system. So this is a trick that you could use. Of course, that's not one that I would propose for you to use, but be aware that this can be a trick that you could see out there. Okay, then let's have a look at the effect of the nitrate concentration. So here's different nitrate concentrations in our catholyte. You can see that mostly influences the current density and the Faraday efficiency distributions. But in all cases, we still have a low urea yield. And you can see that if we have higher nitrate concentrations, this basically blocks CO2 reduction reactions and hydrogen evolution. So we get more nitrate reduction and more products from the nitrate reduction and less products from hydrogen evolution. CO2 reduction, but we don't see a huge effect on the CN coupling variation. Same for CO2 flow rate, right? And the CO2 flow rate is actually less spectacular. You see almost no change with different CO2 flow rates. So, different CO2 inlets in our flow rates in our electrolyzer, they don't affect the CN Faraday efficiency too much. That means that basically our CO2 flow rate is not that important. Actual CN coupling. Okay, another thing that's been well known in CO2 electron reduction and nitrate electron reduction is that cations can have quite an effect on both of those reactions. So if you now look at urea, if we use different cations, so from lithium, sodium, potassium, cesium, we do indeed see that it has an effect, right? So you see the lowest Faraday efficiency towards urea with lithium, and if you go up in cation size, with cesium, we see the highest Faraday efficiencies to urea. And of course, what is known from CO2 electron reduction is that these cations can have an effect on the interfacial pH. They can have an effect on the interfacial water structure near the catalyst, and it can also stabilize charged reaction intermediates on the surface. So this can also be an explanation here where we have a slight enhancement of urea Faraday efficiency with a bigger cation. And if you look at the reaction temperature, again, we do the reaction at different temperatures. We see that we have a slight increase again with reaction temperature going to around 8% Faraday efficiency to urea. Lastly, I want to show you a bit of the different cell configuration. So we thought, okay, well, we've now tested everything in one cell configuration. How reproducible is it in different cell configurations? So we took a couple of cells, electrolyte cells that we have in the lab. So this is a small test cell with a 2.25 square centimeter electrode. This was a standard standard cell, and we took a bigger cell. Here is 10 square centimeter electrode cell system. And you can see that actually all of those have an effect on the distribution of the Faraday efficiency, but not too much, especially for these two, not too much on the actual Faraday efficiency towards urea. You see with the bigger cell that we have a little bit more of hydrogen evolution. This, I think, is due to depletion of reactants if you have a longer flow channel, right? But the eventual Faraday efficiency to urea is not affected. Good. Okay, so basically what we can conclude from this, this study that there is an effect on the operational conditions on urea, but in all cases we see relatively minor Faraday efficiency still to urea. We're not able to reproduce those great Faraday efficiencies that you see from the literature, like the 60% Faraday efficiencies. We go max to like 8-9% Faraday efficiency to urea on a commercial crop-based system. We see the bipolar membranes are the best system, right? Because they allow for stable operation. We see also that catalyst loading, nitrate concentration, and the metal cathodes do affect, but effects are relatively minor. Yeah, we see that the same catalyst can exhibit different behaviors over different cell configurations. So cell configuration that you actually use and using a sort of a standardized cell configuration to test for this reaction actually would be very helpful to achieve reproducibility in the field and to actually advance the field a little bit further. And the last was basically that we show that actually if you use this mathematical trick, you can increase your urea yields artificially. Of course, this is not what we want, but I could also explain some of the very high urea yields that you see in the literature. And lastly, I think most importantly, we really are strong proponents of looking at this from a more engineering perspective. So moving away from all of the nice but complicated catalysts that that are produced, that are tested in different cells, which are very difficult to reproduce. And since there's quite a debate out there whether we could actually reproduce this reaction and how far we can go with this reaction, we're strong proponents in looking at it from a more standardized engineering perspective. So with that, I would like to thank the team, especially Dr. Schlampoels from all the work, of course the ICONIC consortium, and thank you all for your attention.
Thanks a lot for the presentation. So any question, curiosity from the audience? Oh, okay.
Thanks for the nice presentation. I have a question. In one of your slides, you showed when the area of the electrode changes, you get more hydrogen when it's bigger and then more nitrites when it's smaller. Do you have an explanation for that?
Yeah, so I think the hydrogen is related to depletion of your reactants, right? So you have less, you actually use up your CO2, you use up your nitrates as you increase your cell, right? You use them up more. And then the side reaction that is always available is hydrogen evolution from water, right? Because there's unlimited amounts of water. So I think that basically explains why we, if we increase, get a little bit more of hydrogen evolution. The increase in nitrate, that's a good question. I don't have a clear explanation for that one yet, but yeah.
If not, I have one. Discussing about the CO2 flux on the CO2 flux.
Yeah.
You said that there is actually no difference depending on the CO2 that you are using.
Oh.
But this because the CO2 is on the, I would say, on the feed side of the membrane. So they're actually coming out from the other side, and there is the membrane that modulates the CO2 cluster to it. But I try to have different pressure, so by changing the concentration and then the force that drives the CO2 permeation through the membrane.
No, we haven't done varying pressure in the system. That actually would be a very interesting thing to do. What we know from CO2 electrolysis is that this system works really, really nicely. So this is basically a typical setup that we would also use for CO2 electrolysis. So I would not expect that CO2 flux would be a limiting factor, also because we use a porous gas diffusion electrode, and then the diffusion length towards the catalyst side is going to be really, really, really small. I think what this shows primarily is that we have two reactions that are competing, right? Nitrate reduction and CO2 reduction, and we actually need both of them to do the CN coupling. But what you can see clearly is that we have so much more nitrate reduction than we have CO2 reduction. Basically, this is the dominant reaction, and then CO2 reduction is in competition with nitrate reduction for the same active sites on the catalyst. But there's limited amount of CO2 reduction actually taking place, which means that you have to have a very limited consumption of CO2, and therefore CO2 flow rates are probably too important.
Thank you. So I have also a question. Could be that maybe the urea is also forming and decomposing at the same time. It's a reversible reaction going on.
Yeah.
Because for use that all the productions are the same.
Yeah.
I mean, and
yeah, this is a clear concern, right? So urea decomposition is a clear concern.
what I to do this reaction, putting some amounts of urea instead of nitrite.
And then to see whether it decomposes over the. I think we have. I'm not sure. I think we've done some experiments with where we spike the electrolyte with a bit of urea, also to check whether we could actually get the same amount of urea in our quantification. And I think that was quite reproducible.
Okay.
And if I remember correctly, we are now basically under the assumption that urea decomposition can be a factor, but it's not so fast that it would directly alter our conclusion. So basically, if you also look at the Faraday efficiencies, they almost reach all 100% Faraday efficiency, so we're not missing too much product. Over the longer term, it does have an effect. So if you take a sample and you leave it standing for 24 hours and then measure urea, I would imagine that you lost a bit of urea.
Okay.
Yeah.
And last question, from your point of view, what can be the possibility from the point of view of the engineering of the reactor to perform these efficiencies of 8%, 6%?
Yeah, so I think the important trick is to go to a system where we can actually limit nitrate reduction and enhance CO2 reduction so that we actually have more efficiency and coupling on the surface of the catalyst. And this is quite difficult because CO2 electrolysis has a higher overpotential than nitrates. So nitrate is more favorable, nitrate reduction is more favorable than CO2 reduction. So yeah, from the engineering perspective, we can think about systems where we would have maybe a slightly lower nitrate concentration near our electrolyte and can actually boost the CO2 concentration near our electrode surface. So maybe this could be a means to kind of push the balance a bit more towards the CO2. Yeah.
Okay. You discussed, just curiosity, you discussed about the napkin that was not working, then a bipolar membrane.
Yes.
Which is the bipolar membrane that you're using, and you think there is room for improvement for that bipolar membrane?
Oh, there's a lot of room for improvement, definitely. I think we're using the FumaSep systems and the bipolar membranes. They work, but of course, the huge downside of using the bipolar membrane is that it has a huge intrinsic ohmic resistance, right? So you add almost more than 1 volts of potential to the overall cell potential by using the bipolar membrane. So yeah, having actually a bipolar membrane that would limit this overpotential slightly or more, and then having I think what's also a key issue with the bipolar membrane, these are short-term tests, right? 1 hour, but long-term stability of bipolar membranes is still a key issue. Yeah.
If there are no other curiosity, we can take a bit to it. You can move to the next speaker. To Philip Moore from the Technical University of Darmstadt about pilot testing and techno-economic evaluation of chemical liquid combustion. And I told you it's biplex, so go for it.
Thank you for the introduction, and also hello from my side. My name is Philip Moore from the Technical University in Darmstadt, and I would like to use the next 15 minutes to give you some outline of our work on pilot scale testing of chemical looping combustion within the Flex DLC project. Right now, we're still in preparation of these tests, so this slide will actually focus on our prior lessons learned in this field and how they affect now our preparation and our test plans for the BioFlex project. Let me begin with a very quick recap of why we look into chemical looping combustion. Chemical looping combustion typically works as a carbon capture process, typically in the field of a power plant. And unlike maybe the most straightforward form of carbon capture, where you add a CO2 capture facility to extract CO2 from an existing flue gas, chemical looping combustion operates as a so-called oxy-fuel process, which basically means we do combustion, but with oxygen undiluted from nitrogen. For typical oxy-fuel applications, this means air separation unit first. For PLC, we include this in a 2-reactor system. How does it work in a little bit more detail? We have 2 reactors, first one being the fuel reactor, where we enter some carbon or not carbon-based fuel, and this is combusted with oxygen provided from a so-called oxygen carrier. Typically, this is a metal oxide. So for example, here, just exemplarily shown for methane combustion, we have this metal oxide. This metal oxide is reduced, and this way the methane is oxidized, and we get a flue gas stream from this reactor, which primarily consists of carbon dioxide and water, so it's quite easily ready for further compression and storage or utilization. To keep this going, we need a second reactor. In between of these 2 reactors, this oxygen carrier, this metal oxide is circulating, and in the second reactor, the air reactor, we use then air to reoxidize our oxygen carrier particles. There is some limitation to that typically, especially if we look at rather low-cost oxygen carrier materials, which are of quite much interest because they are economically viable and quite easily available. But there we have to expect that this conversion of the fuel is not complete. So we will typically assume to add a small amount of extra pure oxygen in the off-gas stream to fully convert all of the residual combustibles in there. Obviously, this amount of oxygen should be minimized, and how well it works depends a lot on the operating conditions and the fuels we use. So why is this of interest? It's overall quite a more complicated process than normal combustion. But the primary advantage here is that we can get the CO2 separation at a very low energy penalty, at least potentially, because we can mostly avoid the use of quite energy-intense gas separation processes. We can also expect some efficiency benefits from this configuration, because we expect that, especially with tricky fuels like waste materials, that most of the corrosive species included in the fuel will end up in the off-gas from the fuel reactor, while the air reactor off-gas, which can also be used for heat for water steam cycle utilization, is expected to be rather unpolluted, which allows the use of high steam parameters on this side, and therefore also potentially high electric efficiencies. And finally, with the oxygen carrier materials we're currently looking in, we expect a lot of synergies with existing mineral and metal industries, so that either residual materials from such processes can be used as oxygen carriers, or at least spent oxygen carrier from this process can in part be reused in these existing processes. Current state of the art, what is this technology? It's not used commercially yet, but it has been tested on various pilot scales all the way up to 5 megawatt, recently demonstrated in China. With this oxygen carrier material work, at least on large testing scale, being centered around cheap natural ores, mainly ilmenite and other iron ore candidates. And for the fuels, the technology has originally been proposed and mostly tested with different fossil fuels like coal and natural gas. And now, also within the BioFlex project, we want to apply it to residual biogenic fractions and also other waste streams, which are not easily reused in any other way. So for our work in Darmstadt, a lot of our research on chemical looping is centered around large-scale pilot evaluation, which we conduct in a 1 megawatt pilot plant shown here, which mainly consists of two circulating fluid bed reactors, which are used as this air reactor and fuel reactor, and are coupled directly to two loop seals. Our work in this field started already more than 10 years ago with the Eclair project commissioning this pilot plant in 2011, which, similar as the following projects, Acclaim and Success, looked into the details of applying chemical looping to coal, torrefied biomass, and natural gas. More recently, this pilot was also retrofitted or adapted for operation with chemical looping gasification, which is a quite similar process to chemical looping combustion, not aiming at full conversion of the fuel, but actually aiming at producing a nitrogen-free syngas without the need of pure oxygen for, as normally used in a gasification process. And in regard to chemical looping combustion, the recently completed Project Louise looked into the application of CLC with plastic-rich solid recovered fuels, so classical waste materials, which is directly linked to our two ongoing projects in this field, the A-Cloud project and the BioFlex CLC project. As I mentioned before, as the BioFlex project is still for us in a rather early stage, we don't have test results yet, but I will just outline what we can take from the Louise project recently concluded and how this affects our work in BioFlex. So what did we do in the Louise project? We used two pilot plants, one at our project partner, Sintef Energy in Norway at 150 kilowatt scale, and our 1 megawatt plant. We used the quite typical cheap oxygen carrier material ilmenite and a commercially available SRF provided by the Dutch group N+P, which consists to about 50%, a little bit more maybe, of plastic wastes. And we tested this in both pilot plants. And the first takeaway we got from this is that carbon capture, so the amount of residual CO2 emissions from the process, is quite small. So the CO2 capture efficiency in this plant was more than 95% in pretty much all of the test cases in both pilot plants. But what we also had to notice is that the oxygen demand, which gives the fraction of this excess oxygen which needs to be inserted in the flue gas. So basically, it's a measure for the incompleteness of combustion, with 0% would be perfect and 100% would be no chemical looping at all, is quite high for these materials in our tested framework. So here we're talking about oxygen demands on the scale of more than 30% throughout these tests, which is not very beneficial for the technology, because obviously the higher this value gets, the lower is the benefit we have from this CLC technology. At the same time, we've seen some quite distinct tendencies in our data here. Most prominently shown here, the effect of system temperature on this oxygen demand. And what we see across both units is that this oxygen demand distinctly decreases if we operate at higher temperatures. At the same time, there are some limitations to that. We have to consider ash melting. We have to consider agglomeration behavior of the ilmenite and all that. But still, if we operate at higher temperatures than we did last time here, we can expect quite acceptable oxygen demands also for this fuel. What we've also can take from this test is that the scale-up behavior of the process is actually quite straightforward, at least based on this. Right now, still preliminary data. But if we look at the data points from the two pilot plants operating at both 850 degrees with quite similar operating conditions, we see very similar central KPIs for the process, which is a good indication that what we see on pilot scale can also be used for an upscale plant. At the same time, central outcome of this is also that this post-oxidation step for the process is a quite relevant part of the overall chemical looping process when we look at high volatile fuels and low-cost oxygen carrier materials. So this is something we're taking to the BioFlex CLC project, where we now also will include this post-oxidation part more into our research scope when doing the pilot testing. As a second topic, in the Louise project, we also had a look on the potential economics for a CLC plant using this kind of waste fuels and how it can perform in comparison to other technologies. So, for example, one case study we conducted was for an existing 90 megawatts waste to energy plant at an industrial park in Germany. And we had a look at the economic performance when assuming we would replace this plant with a CLC process. And key takeaway here is we were able to determine with our base assumptions some positive profitability, but as you can also see when you look at the accumulated discounted cash flow here, that even though there is a positive net present value in comparison to the investment, it's not a very good investment decision right now to build this plant in the assumed framework of policy we included in this study. But this is the second important takeaway for us here, that for the economic performance of the process, it was much, much more important what we assumed in policy boundary conditions. So especially like negative emission revenues and carbon taxes and also electricity prices, which had a really strong effect on economics. While the CLC related parameters like the oxygen demand level or also the amount of spent oxygen carrier showed much less influence here. And also at the same time, when we compared the CLC process with other carbon capture technologies in this location, so if we assume a framework where we want to capture this carbon dioxide from this plant in some way, then CLC was much cheaper than, for example, amine scrubbing, which is much more mature kind of reference technology for carbon capture here. At the same time, obviously, chemical looping, even though tested on large pilot scale, still comes with higher investment risks because it's not commercially used yet, which is another topic we aim to, or which aligns very well with the scope of our work in Bioflex CLC, where we will have special attention on developing a very flexible process concept, which can reduce this investment risks, this initial ones. But I'll get to that in a minute. Let me quickly outline the overall of the Bioflex project. So first, what we want to do is we want to take the things we learned from the prior tests and again, operate a 1 megawatt CLC pilot plant using different biogenic residue materials, thereby obviously aim to maximize fuel conversion, but also integrate the whole process chain in our pilot testing. So post-oxidation and also to the work of a project partner, the CO2 liquefaction. And then the second big topic for us here is this flexibility in the plant layout. And here, the Bioflex concept includes the development of a plant, of a CLC plant, that can not only operate as a carbon capture plant, but depending on current market situation or the policy framework, can also switch to conventional CFB combustion. So no carbon capture in this mode, but therefore also a kind of safe business case. And therefore, ideally, an easier investment decision for potential operators of such a plant in the future. And as I mentioned, the second big thing for our work here is this post-oxidation part, because it maybe sounds quite easy to just add some pure oxygen in the reactor outlet, but in the end, this will need kind of a separate reactor. And this is something we now include in a more, let's say, sophisticated way, and also in a way much closer to how we imagine this post-oxidation could look like in a commercial plant. So most importantly, instead of cooling away their generated heat just by adding water quenching, we will now have wall cooling, so similar to a membrane wall system, as it could be used in an upscale POC plant. We'll also include much higher ranges for the thermal load that can combust there, so that we're able to operate this plant not only in perfect stable operation, but also during load changes and all that, where we have to expect, at least for short periods of time, high oxygen demands maybe. And yeah, this is currently in manufacturing, so we will commission it most likely next year within our Bioflex or cloud test campaigns. And so let me briefly conclude. Chemical looping combustion, at least from our perspective, seems like a good candidate for the combustion of residual biogenic or waste materials. We can expect quite high carbon capture efficiencies, but the oxygen demand is something we have to address in our next work. And also this investment risk, an important thing, which is also addressed within our work in Bioflex CLC. So this is it from my side. I'm looking forward to your questions or comments. Yeah.
Thanks so much for the presentation. Quite clear. Any comment? Just yes.
Very nice presentation. You're talking about the economics of the entire unit.
Yes.
So have you also considered what happens after the oxygen carrier, which has been utilized? So does it go to a landfill or it is being repurposed? Because if there's a deeper reduction in your oxygen carrier, you can extract pure iron out of it potentially.
Yeah, there was a lot of interesting options there. But for now, for this economic assessment, we try to keep it safe. Let's phrase it like that. So we made rather pessimistic assumptions here. And so for the oxygen carrier, this means we assumed landfilling costs, even though I also think there are much other options and hopefully more promising options than just landfilling the material. But for this study, it was landfilling, which we assumed.
It's very nice presentation. I'm just wondering, I have two questions. First question is, in your conclusion, you mentioned like there's the you need to optimize the oxygen carrier. I'm just wondering, is that because loading of this oxygen carrier is not sufficient? Or that's my first question. And the second question is that this project has been run for like more than 15 years. I just wondering what's the main bottlenecks from the lab scale to the pilot scale? What's the main difference?
Yeah, no, sure. For the first thing, I think for the oxygen carrier, we actually do not plan big adaptations here because we don't. I mean, there is a lot of promising oxygen carriers around, which are tested in lab scale. But when we want to do pilot tests with them, we need this on the scale of like multiple tons of material. And this is an amount that is very hard to store for this, I would say, more sophisticated materials. So there we will again stick to ilmenite, which is pretty much standard, and for which we also know that especially if we look more into the field of biogenic materials, not so much for plastics, it works quite well. So here for bioflex, where we will probably use like mixtures of these materials, we're quite optimistic that this can work out well. And for your second question, the scale up.
Yeah.
I mean, technology is on a quite hard TRL in many fields, but at the same time, on the original field, it was tested with very different fuels from what we do now. And so this is the big difference now. If you look at like the old classical candidates like coals or lignite, the big pilot plant in China operated very successfully with lignite. And there is also most likely some scale-up plan for this based on this fuel. So this seems to be quite far ahead. But with this different fuels, we don't have that much experience yet. So that's why we still have to do a bit more research in this field.
Thank you. Any other question? If not, I have one. You were discussing about 30% of oxygen demand. That is a kind of number that gives you
Yes.
an idea of the efficiency of the process.
Yeah.
Right? What is the same number at lab scale? I mean, in pilot, we are at 30%. If you are working lab scale, what is the? I would
Depends
say,
a lot on the conditions.
yeah.
The tricky part is here in the pilot plant, all or a lot of boundary conditions interact with each other. You cannot just set the temperature because the temperature is based on how good your conversion is. If your conversion is very good, your temperature will be very high. If your conversion is not so good, your temperature will be cold, and this will make the conversion even worse. So it's difficult to compare this with a lab scale plant where you just install electrical heating and then you can operate the process at whatever conditions you kind of like. And so there you can definitely have better.
Yeah, I can imagine it was better just to have an idea of the gap that you need to fill in. With an ideal condition and a real condition. That's the.
I mean, ideal conditions, if we look at process simulations for waste, we did not do like lab scale tests in our group. But so for process simulations, we end up on oxygen demands somewhere around maybe 20%, maybe a bit more, a bit less. And for pilot, you see it was 30% and more. And
okay.
So there is definitely room for optimization. And this does not include like any real significant changes to the overall systems, like different reactor layouts can make a big difference. Different oxygen carriers also can obviously make a huge difference. But yeah, in this kind of framework, from simulations, we see that at least 20% should be is something we can aim for.
If there are no other curiosity, thanks again
Thank you
for the presentation. We can move now to Pamela Kawandi from University of Antwerp. The project is Confetti, and she will discuss about understanding the interplay between reaction conditions and urea electrode synthesis on AG electrodes.
I will be presenting our work that we did on the enhancement of the operating conditions for the production of urea on silver electrodes. So for a quick introduction, I will not go a lot into details, it was already talked about. Urea is a main fertilizer that we use in almost all of our agriculture, and the need for urea will only keep on increasing in the upcoming years due to the increase in the population. Urea is a nitrogen-based fertilizer, and it uses 2% of the global energy to be produced. And it comes from the ammonia reaction with carbon dioxide. Ammonia comes from the Haber-Bosch process, which is a very energy-intensive reaction that causes a lot of environmental problems. So the idea for this project was to synthesize urea in a more green way through electrochemistry. So the Confetti project, the idea of it is to have an electrochemical reactor that uses carbon dioxide that is captured from the air and fed into the electrolyzer, and the electrolyzer would be powered by a solid fuel cell. So my work in this project focuses mainly on the electrochemical reactor, and the first study that I did was to enhance the operational conditions of this reactor in order to optimize it. So the goals were to separate the reduction reactions of CO2 alone and then for nitrates alone before combining them together to check for urea. And the conditions that we studied were first the applied currents, so we did a screening of different current densities. We also tried to change the pH of the electrolyte with 3 basic neutral and acidic conditions. And finally, to try to change a bit with the electrolyte concentration to check how that affects. The cell that we were using was a basic H cell configuration where we used silver electrodes as the working electrode. We also had a CO2 line that was bubbled into the system and a line that goes directly to the GC to analyze gaseous products. The electrolyte that we used was 0.1 molar potassium bicarbonates and 0.1 molar potassium nitrates. We also used the H2SO4 and POH to adjust the pH for acidic or basic conditions, and we applied the current for 15 minutes for each experiment that we did. So starting off, we tried first the neutral pH. For the first set of reactions, which is the CO2 reduction reaction, we noticed that when we screened the current density between -4 and -58, we noticed that the peak for CO forms around -12 milliamps per centimeter squared, and it reached around 40%. While for nitrates, the nitrites was the main product at lower current densities, while ammonia was only formed at the higher ones. When both reactions were combined together, we also noticed that the peak for urea formed around the same peak for CO at -12 milliamps and reached around 20% efficiency, which can be directly correlated that CO formation can enhance is directly related to the CM coupling that forms urea. For the next one, we tried the similar things, but at a basic pH. So for the basic pH, we were constantly adjusting the pH of the electrolyte by adding KOH during the experiments and monitoring it so that CO2 does not neutralize the pH. The surprising thing that we noticed was we didn't detect any CO for the CO2 reduction reaction, while for urea synthesis, we noticed the peak around the same current density at neutral ones. And as for acidic conditions, the selectivity for CO dropped, and we were noticing higher levels of hydrogen, and also the selectivity for urea was dropping. Moving on to the catalyte optimization, we tried to change two new formulations for electrolyte, where in the first one, we tried to lower the concentration of potassium nitrates because nitrites was a major product in most of our experiments. So when we lowered the concentration, we noticed that in the second graph, we noticed that mostly hydrogen was being formed. And that can be linked to the fact that potassium nitrates might be limiting the hydrogen formation, but when we lowered it, hydrogen was mainly produced. And the second formulation that we tried to do was to increase the concentration of potassium bicarbonates to 1 molar instead of 0.1 molar. And there we noticed that an increase in urea was noticed, and the efficiency reached around 30%. So the main conclusions for this part of the presentation was that neutral and basic pH favored the urea formation, while big ones showed more hydrogen, and that CO activation was the key step in the formation of urea. Also that the peak of urea forms around -12 milliamps, aligning with the CO formation or other CO species, and that CO is the limiting step. And finally, that the catalyte tuning showed us that when we lower the concentration of potassium nitrates, we get more CO, but also more hydrogen, which limits urea. But when we raise the concentration of potassium bicarbonates, we had a better nitrite conversion and higher urea. Now, moving on to a different section of this project that we worked on was to test materials for CO2 capture and reduction into CO. These materials were worked on in collaboration with the University Autónoma de Barcelona, and they are the materials that supply the CO2 into our electrochemical reactor. So as an introduction, why did we select ionic liquids? It's because they have tunable physiochemical properties and they have high CO2 solubility and selectivity, but they have some limitations, which led us into using them as a form of ionogels. Ionogels are turned into ionic liquids into a polymer, which this polymer can be used as capturing the CO2 and also into transforming it into a CO in a direct one-way step. So the synthesis of these materials started with first mixing the ionic liquids with a polymer and stirring it for 24 hours at room temperature. Then the mixture was casted into circular shapes in order to form them. And the gels that were obtained look like that. The ionic liquids that were selected were 5 types. The first 2 types were imidazolium-based ionic liquids, and the others were different types. The target of those gels was to capture CO2, but also to electrochemically reduce them. So as a characterization for those materials to study their the properties, TGA showed that upon the addition of CO2, we can notice that the mass of these gels increases, and cyclic voltammetry scans showed that when CO2 is introduced, you can notice a peak in those materials. And further tests showed that the imidazolium-based the based ones had the highest CO2 absorption in addition to the best conductivity ones. Now, moving on to testing those materials and checking if they can reduce the CO2 to CO, we tried to use those ionic gels in electrochemical cell, where we place the gels on a 3D screen printed electrode, commercial one from Metron, which has silver as the working electrode. The electrode was placed in a CO2 saturated medium in a cell, and voltage was applied for 30 minutes. During those reactions, we recorded the amount of CO that was measured, and we noticed also that for the BIMIM and IMIM, the imidazolium-based ones, we had the highest CO current CO efficiency, and it reached around 70% for some of them. And the CO production also reached around 5.5 micromoles per centimeter per hour. Moving on to after the gels proved to be successfully able to capture CO2, we tried to use those gels for also urea synthesis. So the nitrates were added into the composition of those gels, and using the similar reaction conditions, we noticed that the BIMIM and the BIMIM-based ionic liquids had the highest selectivity for urea and reached around 30% for some of them. So this is a nice value compared to other literature methods for producing urea. And finally, for these conclusions, ionic gels were successfully able to capture and convert CO2 to CO. But they provide us with a simpler and lower energy process due to their ability to capture and reduce CO2 in one step. Also, the ionic gels are flexible, stable, and recyclable, which makes them good carbon capture and utilization materials. And finally, that the TFSI showed us the most promising results. It had the highest stability and conductivity and reached an efficiency for CO up to 75%. And that nitrate-containing gels show a preliminary promising way to produce urea with 80% efficiency. And finally, I would like to thank the Confetti team and the ELCAT team for their help. Thank you.
Thanks a lot, Pamela, for the presentation. Any question, comment from the audience?
What was the specific quantification method that you used for urea?
Yeah, so we use the UT method for quantification, but in order to try to limit the variabilities in the errors that might come with this method, we use the internal calibration method, in which the calibration line also includes samples from the sample that we're trying to measure, so that effects of other products such as nitrites or ammonia can also affect the calibration line, and then we can limit the errors that might come from those interferences.
Any other question or comments? If not, not comments.
Yes.
Actually, well, we are preparing such kind of ion gels. We are using PVDF, copolymer for the PVDF, right? That is one of the materials that cannot be used anymore in, at least in few years. Even in membrane science, where PVDF plays a big role, we are trying to move to other materials because you said that you cannot use them more. Are you thinking to use other materials for these membranes?
Yes.
Because to start the technology with something that you know that would not be used.
Yeah, so those materials are not the most sustainable ones, and for now, for the tests we did, that was the option that we started with. But for future tests, we will definitely think about replacing it with other ones. But yes, I'm aware of them not being very green.
Okay, and another question is about the mechanical stability of this ion gel. I got one from Gonzalo, so I add in the lab. And they're quite tricky to handle already when they are like 2 centimeters square of. So if you need to scale up, what are the possibilities to scale up such kind of materials in bigger size to be using real industry?
Yeah, so for now, they are very fragile and hard to deal with. But I think for scaling up, working more on adding maybe an additional polymer to them to maybe increase their rigidity might help. But the effect of that has to be studied and see which polymers can affect it.
Suggestions, questions? If not, think we can go. Thanks again
Thank you.
for the presentation. I think we can close the section, go for lunch, and I'm giving you the. No, you
Not
get.
really. I mean, first of all, thank you for sharing the session. Yes, in principle, we can go for lunch, but we would like to ask the project coordinators, and since you are project coordinator, to stay a little bit longer because we want to take a picture of the coordinators. For the rest, you can enjoy the lunch in 4 minutes.